great pleasure to introduce a good friend and very distinguished researcher and professor, Dr. Robert Heath from the University of Texas at Austin. The title of his talk, as you can see, is Vehicle to X Communication Using Millimeter Waves. As most of you know, that's very near and dear to my heart, and I'm very eager to hear this talk. So he's an endowed professor at Texas. He's a fellow of the IEEE. And I found out last night he has 33,000 citations, which is rock star unbelievable. I'm like a small fraction of that. But
did you check this morning? I think it's 34 now.
It went up overnight, did it? So I'm not going to belabor the point. We're just really happy to have him here. And so I encourage you to have an engaged participation. If you have any questions or comments, please let us know. And we'll have also an answer period at the end. So without further ado, Dr. Robert Heath.
All right, great, thank you. All right, you have okay, so we got the lapel mic going here. So yeah, so I'm pleased to be here to talk about a topic that's really interesting, I think, and I hope that you find it intriguing as well, which is about using millimeter wave for vehicle to X communication, where X is vehicle or infrastructure or person or really anything else that a vehicle might want to talk with here. And then this is supported by a number of sponsors. We are required by the state of Texas to list our sponsors on the talk. So if I say something that you think I'm biased, you know that I might be, being paid by these folks up here, which indeed I am. So first of all, I want to give a little bit of motivation for, why am I a wireless person up here talking about cars? Well, the obvious answer is that cars, they're really cool. And I want to be cool, and so that's basically it. But this is an opportunity where we can actually take two things that are really cool, wireless plus vehicles, and put them together. So the motivation for this talk really comes from the development of 5G cellular, which is happening right now. And so 5G is 5th generation. It's the next evolution of cellular networks. Everyone in here has at least one phone with them right now that is using cellular. And one of the features of the next generation cellular is that it is going to be designed to, of course, offer higher bandwidths and lower latencies and all kinds of, benefits. But in particular, it's being designed to serve new classes of applications. And in particular, there are 5 that have been identified: automotive, e-health, energy, media and entertainment, factory of the future. And so these are important because what's happening is people that sell cellular infrastructure or cellular devices are realizing that if we all have a cell phone, who do we sell more cell phones to? Well, okay, they can make our cell phone battery stop working after 2 years, encourage us to get a new cell phone, make the phone stop working for God knows why, right? That only goes so far. And so they're realizing, hey, what about other stuff? Well, what if I could sell a cell phone to all of the vehicles? Ooh, that's another opportunity. What about if I could sell cell phones to all the robots in a factory? What if everyone had a wearable cell phone plus? Anyways, you get the idea that this is, an opportunity for these businesses to make money, and it's also an opportunity to design the system to support the specific features of these different vertical industries. And the one I'm going to focus on today is automotive. So there are a lot of trends right now in vehicular systems, and one of them is automation. And so we're seeing, as vehicles become more automated, first of all, they're becoming automated because they're being endowed with more sensors. So you have the ability, like a radar, for example, to follow the car in front of you on the highway, adaptive cruise control. You also have like a short-range radar maybe to detect the presence of a pedestrian or to avoid backing into a mailbox, something like that. There's also increasing amount of communication. So a lot of vehicles right now have like OnStar or something similar where there's some kind of communication back into the cellular system, maybe back to the factory or maybe for emergency response. And then we're also seeing right now that these two functions are being put together to support higher levels of automation. And by automation, so what we're going to do is we're going to have vehicles that can drive themselves some of the time or part of the time, or take over some functions from the human. Then they're going to be safer, and then the transportation will be more efficient as we go to higher automation levels. Now, there's a lot of discussion, and there's some subtle differences in terminology that I want to talk about. So most of you are probably familiar with autonomous vehicles. That's really been a hot topic. Let's say like the Google car, for example, Delphi, Uber, Apple is starting to test a fully autonomous vehicle here. So what autonomous really means is that the vehicle is operating completely independently. It's not communicating with anybody else. It's driving itself, but it's only using its onboard information to do that. Now, a connected vehicle is a vehicle that has communication capability. Now, it doesn't have to be autonomous. It could still be driven by a human, but it has the ability to exchange information with other vehicles. So, for example, you could get a warning from the vehicle in front, I'm braking quickly, apply your brakes. And the human could read that warning and apply the brakes. Or if the car had a little bit of automation, the car could apply the brakes for the human and stop in a faster time. And so automation is actually a term that's used to denote different levels of taking control over the vehicle from the human. And it includes at one extreme fully autonomous, and then another extreme it's fully like driver assist, or in fact just driven by the human there. Now, connected and automated are two different things. So a car can be automated or autonomous and doesn't have to be connected, but I'm going to argue that having connectivity is actually going to make automated driving better. Now, just a little bit of background about automation, because I think this is primarily an ECE audience, and so this I think is good stuff to know. So there's these different levels here. This is the ones from the TSA document here. And so no automation, level 0, full driver control at all time. This is like where I am in my 20-year-old crappy Honda Civic right there. And then the driver assist is these levels in the middle. And the driver assist, what's happening is some functions can be taken over by a computer in the car, and perhaps one function or two. Like maybe the car can apply the brakes but cannot steer. Or maybe the car can apply the brakes and steer and take evasive action. And so that's examples of level 1 and level 2. And then self-driving cars would be up here at level 3 and level 4. And level 3, you can imagine a vehicle that you get on the highway and it takes over and drives for you. But then when you get off the highway, you start driving again. So that might be like a limited self-driving automation. It also could be the case that the car tells you to take over if it gets confused or something. And then the level 4, the fully self-driving automation, is where the car is driving itself all the time, and in fact, you are not even allowed to take over because there's not even a steering wheel in place. And that's like the holy grail for the design of automated vehicles here, because if we can get rid of the steering wheel, then the human drivers can really focus on what's important to them, which is, watching YouTube videos, checking Facebook, doing email, whatever it is you want to do on your commute to school or to work or to the store. So you'll be able to do whatever you want. Now think about if you're at level 3 here, you're watching a really enticing YouTube video, the car gets confused and is like, hey, by the way, you might want to take over because we're going to have an accident. So, you got to sit there, you put your coffee down, you put your YouTube video down, then, you start looking around, oh shit, and then you grab the steering wheel, that kind of thing. So clearly that, actually the level 3 is potentially the most difficult of all of these to implement here. And now, there's a few myths surrounding automated vehicles. So the first is that they can be fully autonomous. And this is true. I mean, they can be autonomous, but I don't think that that's very efficient. And then I'm going to argue a little bit why that is here. But essentially, if vehicles are fully autonomous, so suppose that you're going down a road and you're going and taking like a very sharp left-hand turn. And it's a blind turn. You can't see what's around you here. So if you're not an autonomous vehicle, you have to slow down a lot because you can't see around the corner. So you got to slow down and very carefully peer around the corner and then keep going, right? But if a car is right in front of you going, well, that car slows down, starts peering around, and it tells you, hey, it's all clear, put on the throttle. And so then you kind of cruise around much more quickly here. So autonomous operation is great. It's also nice if there's no other cars around, but if you've got other cars around, why not use the information they're generating? The second myth, and this is one that is more pervasive even, is that infrastructure has no value. So people are thinking that automated vehicles, if they're connected, they should talk directly to each other, and I don't think that's the case. And so I'm going to explain two of these things here. So here's the example here. Some of the reasons that communication is useful. I think the main one is that you're expanding the sensing range, your ability to sense the environment. when you have communication. So, the vehicle over here, by communicating with the car over here, now maybe it knows what this car sees, and this car sees, a car coming around the corner here, right. So this information can now be broadcast to me, who I would otherwise not be aware that there was another vehicle coming. Now, this is important because in this example, this vehicle doesn't have communication capability, and so the other vehicle is sensing it, broadcasting that information back. Of course, we would like that car to have communication capability as well, broadcast its own intentions. And you can also interact with vehicles at different automation levels, so bicycles, pedestrians, old cars. Are we going to get rid of those when vehicles are fully automated? Probably not initially, maybe later. So if you have the ability to communicate and sense, you can distribute that information. And things like coordination. So if you want to travel efficiently on a highway using platooning, so many cars can pack very close together. Think about like you're tailgating the person in front of you, but everybody's tailgating everybody else, but in a safe and efficient manner here. And so that reduces the gap between vehicles. You get more vehicles on the road, less congestion, reduced commute times, generally increased well-being in society here. So communication, I think, is really critical and is not being investigated enough in a lot of the work on autonomous vehicles. The second is infrastructure here. Now, to be fair, remember, some of the people funding me do make and sell infrastructure. But aside from that, I think they're doing it because my story is compelling. And I'm not telling you that because, what they're saying is compelling here. But I think the infrastructure is really valuable. So the infrastructure could be endowed with sensing. So if you think about it here, so if you've been to the airport and there's an air traffic control tower. Now, I became a pilot last summer, and so I learned a lot about this here. Air traffic control tower, the people sit high up. They really don't set high up so they can be closer to the planes. They actually set high up so they can see where the planes are on the ground, because they have a bird's eye view there, because it's very hard for the planes to see each other on the ground. And so for the same logic, the base station having sensing can look down and can see the vehicles and not be obscured by trucks and trailers and people. So it can get a bird's eye view, and then it can package that information and broadcast it to all the people. It can be used for a lot of other functions as well to do better navigation. It can help coordinate through intersections. I have a colleague at UT Austin, Peter Stone, and his big thing for the last 15 years has been getting rid of traffic lights. And he's been doing a lot of research on that. And if you have infrastructure-based communication, you can do that. The infrastructure can take over. It's like a handoff. You get near the intersection, the infrastructure is like, okay, I'm going to take control of your vehicle, and then it slows down and speeds up so that you can go through the intersection without colliding into anybody else here. So I think infrastructure is really valuable here. Now, a couple things about communication. So let's see here. Yeah, here we go. So communication for driver assist. So this is just an example of where communication helps in the lower levels of automation. So this is a case on, this is very important in Texas because we have a lot of rural roads. And it turns out there's a huge number of fatalities due to passing. So the typical scenario is you're following behind a rather large vehicle, is going too slow, very impatient, want to get around it. So you cruise over into the other lane, and then boom, whack, you get hit by a car, and of course, it's high-speed collision, people die. And so here, the vehicle in front could sense the vehicle, could tell the person behind, hey, don't pass. You just get a light that says, don't pass, warning. Or it could be that the vehicles communicate, and then you realize not to pass. So you could just get an information flag that tells you not to do something stupid. So that's one way that communication can happen. Communication for full automation, though, can do much more wonderful things. So we can, one of the things really important in automated driving is map information. And I don't mean like Google Maps, I mean like 3D depth maps. So it's very hard for cars to know where they are. GPS is only accurate for meters. And even though you can get an expensive GPS that does decimeters, it doesn't necessarily work everywhere. If you're in an urban canyon, you got a lot of multipath, you don't know where you are. And so by having a 3D depth map, you can use radar and LiDAR to kind of ping and say, okay, that wall is over here, this wall is here. I know from my map that I should be about right here by the podium. And that information can be updated on a very fast time scale. So I could have someone walking in front of the environment, the base station could monitor everything, figure out where that person is, update the map, broadcast the map to all these people here. And that's only really feasible if you can communicate a lot of information, a lot of sensor data. So that's some of the advantages here. Now, to give you an idea of the data rates, I mean, you need on the order of hundreds of megabits per second to gigabits really to exchange the sensor data to make these higher levels of automation happen here. So high data rates are important. Now, low latency is also critical because if you get the information that there's someone walking across the street 4 seconds too late, that is enough time for you to have a fatal collision. So latency is really important here as well. And this is one of the reasons that this problem is extremely challenging to provide communication for the vehicular setting here. Now, this is not just about automation and safety. There's other benefits of communication as well. One of them is traffic efficiency. So if you can do platooning, you can coordinate the transportation better, make more space for vehicles, get rid of traffic lights, or retime the lights in a very dynamic fashion. You can get to work faster. That's good for your advisor, or it's good if you want to take off early, have a beer. So traffic efficiency is critical. And then there's also the classic infotainment. Many of you probably don't have kids, but if you have kids, you realize that entertaining them in the back seat is crucially important. And it's nice to be able to provide that entertainment as well. So some of the questions I'm going to try to address in this talk. What are the sensor rate requirements? What are the communication capabilities with current approaches? And then where is the interesting research challenges? In particular, where does millimeter wave fit in with all of this? So first off, on the sensing side, so these are some of the sensing modalities that you see in cars right now. There's radar, camera, and LiDAR. And then the ranges of these devices, these are automotive types of products, are on the order of 100 to 200 meters. And this is clear weather, outdoors, no one around, totally flat road. If you're in a congested area, well, what can you see? What can the LiDAR see? Well, the LiDAR sends a laser and gets a reflection off of a vehicle in front of you, and you can't see beyond that. So when you're in a very congested area, the range of sensing actually reduces quite a bit, and that's one of the reasons to go to the infrastructure on putting the sensing on the infrastructure there. So these are the kinds of sensing that are popular right now. Camera could be still frame or it could be video. Either one. And typically, the automotive applications of video are very lightly compressed because you're applying machine learning algorithms here. So you need high data rates. And so here's to give you a sense of the data rate requirements here with radar, cameras, and LiDAR, and the update rates, so the latencies. So the data rates can be, for radar, as small as megabits per second. For cameras, it can be hundreds of megabits, depending on the kind of compression you're using and if you're using predictive video or not. And then LiDAR depends on how many beams that you have and the refresh rate. But it's on the order of hundreds of megabits per second. Now, this in itself might seem not too bad, but remember that if I have a forward-facing radar, what do I do behind me? Well, I need a rear-facing one too, and maybe I need another on the corner. The Google vehicles have 6 radars. So multiply these numbers by the number of devices you have. So maybe we need 6 radars, maybe we have 1 LiDAR and 5 cameras, and you start adding up all the data, you start to get into hundreds of megabits per second, if not gigabits, and that needs to be delivered in a timely fashion. So let's look at the state of connectivity in vehicles. Well, the question that we wanted to address here was, can we exchange all that sensor data using conventional technologies here? And so the current approach for wireless connectivity is called DSRC, Dedicated Short Range Communication. It's actually based on 17-year-old wireless technology. It's not an especially new standard. It has just now started to be implemented in high volume. Not even high volume in the US, but low volume, like Cadillacs right now are being deployed with DSRC. And there's a whole standard. It supports all kinds of different applications like forward collision warning, do not pass, and different capability here. Because it's based on Wi-Fi, and it's based on Wi-Fi using 10 megahertz channels in dedicated spectrum. The max data rate is 27 megabits per second, but that's actually pretty high. Normally, it's closer to 6, if not 1 megabit per second. So this standard does not support the ability to exchange sensor data. The one thing that it does do, which is very important, is it does support what's called a basic safety message, where the vehicles can broadcast 10 times a second their position and velocity. So it does provide a way for other cars to know what's happening around them, but it doesn't allow you to do all the cool things that I talked about earlier with exchanging the high-resolution data. So that's the current technology, and this technology is just now being deployed. And most likely it is going to be deployed to to a large scale in the next few years, unless an alternative comes, like based on cellular, for example. And so, yeah, this is the just the examples here. So the basic safety message, collision threats, vehicles can either notify the driver or take control depending on the exactly the message there. Now, current cellular technology, prior to what is called 5G, the 4G is evolving. And there's something that's just been released, which is called LTE V2X, which is an enhancement of the LTE 4G cellular service to support some of the vehicle connectivity, in particular to reduce the latency, to allow vehicles to talk directly to each other. And then it's done through the cellular infrastructure, which turns out to be very reliable, because a lot of the places we want to have cellular for safety applications, there's a lot of people and there's a lot of base stations. And there's a lot of infrastructure, and so it's very efficient actually to use the infrastructure in these applications. But the problem with this is as follows here. So if we look at the LTE V2X and the D2D and the cellular mode, the specifications differ, but in any case here, the data rates are just not very high. So with cellular right now, we're talking 50 megabits per second or so to the cars. And hopefully that's in a reasonably reliable way. The coverage is quite good, and the mobility support is high, but the latency is with DSRC, the latency can actually be like a millisecond, but with cellular, depending on which mode you use, it can be tens or hundreds of milliseconds, which may actually be too high. So the main issue here is, one, the really high data rates are not supported, and two, the latency with high data rate is also not capable there. And then this is an issue, so if we look at even the mode of operation where the vehicle stops at home at night and uploads data, and then the next day it gets a new download, something like that, that's on the order of several gigabytes a month, which could easily exceed your current plan, right? But automated vehicles, according to one study, can generate up to 1 terabyte of data during 1 hour of driving. Now, of course, you probably don't want to save all of that data, but it's actually not obvious what data to save, especially when you're applying all these different signal processing, machine learning algorithms on top of that. So maybe you do need to save a lot more than you think. And what if we develop a new algorithm 2 years from now? Well, if we had that data, maybe we could train it and do better. So basically, the current technology doesn't support the high data rates. So now I'm going to tell you about another alternative. It's called millimeter wave. So millimeter wave refers to the frequencies that are from 30 to 300 gigahertz. So it's high carrier frequencies, much higher than we use in cellular right now. And the benefits of going to millimeter wave are that you get communication channels that have a large bandwidth. And so if you have a large bandwidth, it's easier to get a high data rate because you have spectral efficiency multiplies the bandwidth. So for reference, wireless LAN, the 11N, typically uses 20 megahertz of bandwidth. And 11AC, which is the new version of wireless LAN, you can get up to 160 megahertz. There's like an optional even 320. But the wireless LAN that operates at millimeter wave gives you 2 gigahertz of bandwidth with peak data rates of gigabits per second. So that's so millimeter wave is really a technology that's just after peak data rate. That's the main motivation for millimeter wave. Now, one of the things that happens when you use millimeter wave is that the antennas get small. And that can be a problem because you start capturing less area, and there's this general belief by a lot of the population, we're talking the population that knows what wireless is, okay, that millimeter wave isn't very efficient. But if you use antenna arrays, then you can create a large effective aperture, and you can focus the energy that you're sending towards the receiver, as well as you can focus where you're listening at the receiver. And so the combination of this two effects is called array gain, and you get gain at the transmitter and receiver, and you can actually overcome the shrinking aperture effect, and you can get a really high SNR so that you can support huge bandwidth. And that leads to this idea of what's called adaptive beam steering. Now, the gains you get from the directive antenna only happen if you know where to point it. So if you don't know where to point the antenna, then you don't get the gain because you're pointing in the wrong direction. So with in the mobility that's required in a vehicular setting, you have to adapt and adaptively point the beam. And that can be really challenging because cars are moving at a high velocity here. But the main thing is that, so millimeter wave, it offers the means to get high data rates, it offers the potential for low latency. in one package here. So millimeter wave seems like a very attractive solution for automated cars. Because of the high data rate, we can exchange the sensor data. We can do, infotainment. You can do virtual reality to the kids in the back. That's amazing. Joint communication radar, we can sense and communicate at the same time. And then we can also do things that are where we're combining sensing and communication in new ways. And so my opinion is that millimeter wave at this point is the only viable approach for high bandwidth connected vehicles. Maybe someone will come along in the future. There's a terahertz. I guess that's possible, right? That would give us even more bandwidth, but lower range. Or maybe visible light or X-rays, who knows? Maybe in 30, 40 years we'll have another solution. But millimeter wave for right now, I think is the key solution here. Now, millimeter wave could be realized in several different ways. So first of all, it could be done in 5G. And that's actually why I started off the whole talk, right? Is that saying that automated vehicles and is a big part of the development of 5G. So that's actually where we could see millimeter wave for 5G. We could also have dedicated millimeter wave V2X, and that may seem crazy, but Europe already has a whole gigahertz of spectrum for V2X, 63 to 64. They've already got it. We could maybe get it too. That's another place we could get millimeter wave for V2X. We could also modify 11AD. We already have a millimeter wave standard that operates in the unlicensed band from 58 to like 64 gigahertz. The DSRC is built on an unlicensed standard, so maybe we can modify that and use it for vehicular communication. But I think of all these options, the one that's really most attractive is 5G. And the reason is that we're going to be deploying base stations anyway to support consumers for all the other applications. And so why not support the vehicles too? So I think it makes a lot of sense to support automated driving using 5G cellular. Now this is a snapshot of some different, both existing millimeter wave LAN standard, that's 802.11ad, 11AY, which is being developed, and then some 3 possible 5G millimeter wave standards. And you can see the bandwidths and the peak data rates here. And so really we're targeting, anywhere from 1 to dozens of gigabits per second of data rate. And this is just with generalizations of existing technology, not incorporating what you all might be working on in your research, which could push this even further. So the net is that going to millimeter wave, we're going to get a 10 or 100x on the data rate. And that's going to make this vehicular automation happening here. Now, what I see happening is that we're going to use millimeter wave for all kinds of different things. We're going to use millimeter wave to communicate sensing data. We're also going to do sensing at the base station so we can fuse the data there that we get from the vehicles and also combine it with the sensor data that's at the vehicles. And there's a lot of different things that we can do with millimeter wave as well. There's a lot of opportunities actually for machine learning. I know that's a big topic of research these days. There's a lot of predictability in the way that vehicles ride. Like this might be a bike lane, so the communication system, sensing system could learn, hey, bikes travel in this lane, let me just check there's a car coming, make sure there's no bike. So there's a lot of predictability that can really be exploited here to make the driving more efficient, but also to make the millimeter wave communication more efficient. So for example, if I know that a truck is driving by and is going to block my communication path, I can set up an alternate path. I don't have to wait for that path to be blocked. So we're seeing this new synergy between sensing and communication that has never happened before. And so I think that's really exciting, and that's a big topic of my research these days. So I'm going to wrap up here with another 45 slides on designing a millimeter wave V2X system. That was a joke. It's not 45 more slides. This is like a totally dead audience here. This is all right, at least there's something happening. Some people are awake. I wanted just to give you some of the ideas of why is this interesting? Why is it challenging? Why is working on millimeter wave different? Now, I used to get this question a lot because the natural accusation is that, as a professor, your main objective is to, let's see, what do we do as professors here? We teach students. No, we don't do that. We publish papers. We bring in grants for the university, money for the university. We write papers. We train students. But in the process of training students, we write papers, they write papers, and so on. And so there's this thought that, hey, millimeter wave, we're just going to take whatever we did at low frequencies and call it millimeter wave, publish those same papers again, and increase our citation count another 10,000 or so. And that, unfortunately, as appealing as it sounds, unfortunately, we cannot do that because even though the abstractions that we learn about communication, like if you've taken signals and systems or digital communication, there's a certain way you develop to think about a communication system that doesn't depend on the frequency. So the way I communicate at 2 gigahertz is similar at 28, is similar at 72. That's all true. The thing that's really different, one of them is that the propagation channel is actually not the same. I mean, I don't mean that Maxwell's equations stop working. That would be kind of crazy. But because of the small wavelength, things like diffraction are not as significant. There's a lot more sensitivity to blockage. So I can block very easily a millimeter wave signal, and yet at 2 gigahertz, I have no effect. So the channel model actually is a bit different. The topology is also changing. There's a lot more mobility, and the effects of mobility are more pronounced at higher frequencies. So that's one of the challenges. And then there's also this issue of blockage. And finally, the fact that we're using these directional antennas, which we don't use at lower frequencies. So the way that we use the antennas is different. The need for mobility, the sensitivity to blockage, and the differences in the propagation environment mean that we can't just do what we were doing before at 4G and just roll it into 5G, unfortunately, here. But that's good news, because if you want to do like PhD in this area, the fact that there's problems that have not been solved means that you can perhaps write a nice paper, defend your dissertation, graduate, get a job, et cetera. So I think that's good news here for all of us. Now, I'm going to give you a sense of some of the intriguing research challenges that are, that come up when you get into millimeter wave. And those of you that have studied wireless will be familiar with this one here. So there's a concept that's called coherence time. And in a wireless system, that's roughly the time between when the propagation channel is, let's say, sufficiently different. So maybe like 5 milliseconds, 10 milliseconds, 100 milliseconds. And this quantity depends on the velocity of the things moving in the environment, the vehicles. And it's an important piece of information because the coherence time tells you how often you have to retrain the channel. So if the channel changes 1,000 times a second, I have to estimate it a lot more frequently than if it changes 10 times a second. And the general wisdom is that, well, as the Doppler goes up, as the velocity goes up, the coherence time gets smaller. So that's something that we know. And then as the carrier frequency goes up, the wavelength gets smaller, and so you traverse more quickly through different waves, and the coherence time also gets smaller. And so the feeling has been, man, millimeter wave will never work because the channel just changes too much. We can never estimate it in the time. And we were thinking about this for a while, and we were thinking, gee, there's all these wireless systems that work. I mean, we're able to communicate with satellites. They're going really fast. I mean, we're able to communicate with airplanes to ground. I mean, we all know that our phones work on the airplane. Just don't tell anyone I told you to turn it on, but it does work. And somehow, right? So a lot of these systems, the way they work is that they have like a pointy antenna, like I was describing. Like satellites, you have that big dish antenna, and maybe it rotates along. And when you point an antenna, what you do is you focus on a subset of multipaths. And the problem with Doppler is that when you're walking around or when you're driving, you get multipaths coming from different directions. And if I'm walking, the multipath here has a different Doppler shift than the one here. And so that difference in Doppler shift is what makes the channel change a lot. But if I focus on one path, I can actually eventually have just one single propagation path that has just a Doppler shift. And I can fix that with frequency offset correction. So in theory, if you can use a very pointy antenna, the coherence time actually goes to infinity. You never even need to estimate the channel. That's kind of like the theory. But anyone who's like engineered a wireless system, you probably realize, well, of course that doesn't work. And why doesn't it work? Well, you got to know where to point the antenna. So in this example here, I mean, if the antenna beam width gets very narrow, then a little bit of perturbation, I start pointing in the wrong place. It's kind of like pointing the laser pointer, here. I mean, it's very hard to point because the dot is so small. And a little bit of mobility, it wiggles all over the place here. And so we developed an analytical framework for trying to understand this effect, and we were able to show that there's an optimum point. So if you include this pointing error in addition to the Doppler and the effects of the antenna pattern, there's like an optimum beam width where the antenna's pattern is pointy, but it's not too pointy. And in our case, that ended up being about 3 degrees, which is frankly still really pointy, but it's not like 0.1 degrees. And then the other thing that we did that was interesting was we showed that the underlying geometry in the problem, it actually changes very slowly. So for example, in a millimeter wave system, suppose I'm communicating by reflecting off of this wall. Well, as I'm walking along, I'm still communicating off that wall, The angle of incidence to the wall changes a little bit. But more or less, I'm pointing in that direction there. And so we can show that the variability in angle is actually much slower than the variability of the wavefront itself. And so that means that you don't have to repoint the antenna nearly as much as people had thought. And as a result, the millimeter wave has the potential to work very efficiently in high mobility, high Doppler, which is exactly the vehicular setting that we wanted to attack here. So one of the things that we've been doing, so generally in millimeter wave, it is a challenge to figure out where to point the beam. So if you have again, back to laser pointer, I apologize for doing this. I hate the green laser pointer, but that's what I have here. It's really bright. So if I'm trying to find a square, like a 1-inch square on this wall, what do? Well, I just keep screwing around till I find the point, right? That's called like a beam search. And it's very inefficient because the narrower the beam, the more places you have to try to point. Now, in thinking about the automotive setting, what did I tell you before about DSRC? DSRC has the ability to broadcast position. So the vehicles can all talk to each other and say, hey, here's where I am. So why can't the base station listen to that? The base station can have a roadside unit. DSRC roadside unit costs $300. Base station is much more than that. Plug that guy into the base station. Now the base station knows where all the vehicles are. And if it's setting up a millimeter wave communication link with a vehicle, instead of trying the beams all over the place, it can point beams where the vehicles are. And maybe it doesn't get it right, but a lot of the time it will get it right, and then it'll save you a lot of overhead. And so this is something that we've been looking at in my group, has been using position information to help the beam pointing. Now it's kind of an obvious idea because, of course, if we have kind of like line of sight and we know where the transmitter and receiver are, I mean, we can easily point the beam. But people have not really thought about combining these two communication systems together in this way. This using the sensing, the information I'm deriving from DSRC to make cellular communication better. That in itself is, I think, the cool idea here. Now, we took this one step further, and this is an intriguing idea that we call inverse fingerprinting. So the idea is that about 20 years ago, people were interested in developing means for doing position location for cellular systems, E911. It wasn't necessarily going to be GPS. And so what they found was that the multipath signature, which is the angles, the delays, are kind of unique as a function of location. So if I go through the stage and I measure the multipath profile between me and the transmitter, let's say the transmitter's over here, and then I measure it over here, and I measure it over here. So I create a database which has position and multipath signature. And now I go over here and I turn my phone on and I measure the channel and I query the database and it tells me my position. That's the idea. Now, of course, it's not perfect, but it gives it to me within a reasonable precision. And that's called fingerprinting. And what we do is the reverse. We take that same database, but we query it based on location to determine multipath signature. Because if I know that information, I know that, okay, there's a reflection here, and maybe there's line of sight here. So I can try this, and this instead of communicating everywhere at once. So it's about making, instead of trying to point my little laser pointer here all over the place, I'm going to focus on the 3 places I know where there's signal. Okay, there's like here and over there. I'm going to point it into your eyes there. That's bad. And so it improves the efficiency by about a factor of 100. And so that's also nice. Now, what about other things here? Look, sometimes there's a big fat truck here in that lane, and it blocks the path to this vehicle here. So that one path that I thought was good isn't good. Well, I'm going to try several paths, so it's okay. And so what I do is I build this database by making measurements at different times of the day, in different locations. And based on that, then we have data that we can use, and you can use, it's really like a basic machine learning classification type of an algorithm that you can use to estimate the position. And again, we're not trying to get the, we're trying to estimate the promising multipath directions. We're not actually trying to estimate the best one. We're going to do that as a second step. This step is just to get the good ones. And it turns out that what we're working on right now is relating this problem to recommendation engine. So the classic Netflix problem is, you rate a few movies, a whole bunch of other people rate different movies, and Netflix wants to figure out how to recommend to you new movies. So we can actually pose that problem here. So as a function of location, I want the system to recommend beams for me to try based on incomplete information obtained from other places. So this actually is pretty exciting. I'm working with a guy in machine learning at UT Austin to try to quantify this, and we're using some nice mathematical tools related to matrix completion. And it seems like a really cool application of machine learning and wireless. Now, another thing here. So if I'm putting sensing on the base station, what can I do with it? Well, if I had a radar on the base station, what would the city do with that information? Well, if they are the police, they probably want to figure out how fast people are going so they can give out tickets more efficiently. That's maybe a little bit cynical. The city itself might want to know just how many cars go by at a given intersection at a particular time of day. That information is very hard to collect. Most places in cities, at least in Austin, they don't have cameras. And so the only way the city knows how many cars go through an intersection is they go and they throw out this little rope thing across the street, and then cars drive over it and create a bump, and they track that bump. And they do this like maybe every 2 years. So they have no real dynamic way of like tracking transportation. So having the sensing on the base station, you can actually collect a lot of valuable data for the city, aside from stuff that they might want to use for giving us tickets for not speeding, of course. Actually, by the way, a nice thing about radar is that you can't identify people on radar. So I think people would be more comfortable having radar in principle than having a video camera, like in London, where you're being videoed everywhere all the time. But what about, can we do something else? Well, back to the position argument. If I have a device at the base station that's tracking cars, why can't I use that information to help my millimeter wave communication? Or why can't I use it to detect a blockage here? So we have grandpa here is about to cross the street, and he's patiently waiting on the curb, but he is blocking our millimeter wave signal. So we can use the radar to detect that and then take evasive action so that we can communicate with the car, perhaps by pointing to a different antenna or perhaps handing it off to a lower frequency. So it allows us to do the millimeter wave communication more efficiently and solve one of the key problems, which is how to deal with blockages. And again, it's a really new idea to use sensing to support communication. I mean, there's been a little bit of this in some military applications, but it's more about using the same hardware for both sensing and communication as a way of saving space. It's not so much about using one to help the other. And so we've done some work on this where we use the radar, not the position, but the raw information from the radar to help us with the millimeter wave communication configuration. So it's an intriguing idea. Another thing that we've been thinking a lot about, so I started also working on radar, and we have this 802.11 standard that operates in the 60 gigahertz band for communication. Now, up at 77 gigahertz, that's where automotive radar sits. So automotive radar is so close to the millimeter wave wireless LAN. And then we're thinking, well, can we do communication at the automotive radar band, or can we do automotive radar in the communication band? So we've been looking at, can we modify, or can we just use straight away 802.11ad to do radar? So the idea is that you could be communicating with the car in front of you and listen to the echo and determine its position. Now, you might be thinking, if you're communicating with the vehicle, it just tells you where it is. Why on earth would you want to listen to the echo and determine its position? Well, I mean, what if the car in front of you, the GPS isn't working? What if it tells you the wrong position? What if it's been hacked? It's a way of getting a lot of trust there. And believe me, if you're cruising around 60 miles an hour, you want a high level of trust. You don't want to rely on, this is working 90% of the time. Well, then 10% of the time you crash and die. That's not good numbers for us. So we've been looking at combining, so using the existing waveform for communication and radar. And then there's a lot of interesting things. So at some point, you might want to change how the communication protocol works. Because the problem here is that I can see the car in front of me, but what if I want to check where the car is in the next lane over, but I'm not communicating with it? Well, maybe part of the time I scan over there, do a little radar, then I come back and talk to the car in front of me, or I talk to the base station, scan some for vehicles, go back, talk to the base station. So we've been investigating this concept, and I think it's quite interesting. I've also been looking at trying to make these things work. Now, admittedly, a lot of what I've told you, we're writing papers on this. There's a lot of cool math. There's MATLAB experiments, but there's not been enough data. And so in my lab, we have about more than $500,000 of equipment to do millimeter wave communication with phased arrays, with direct communication links, we have the ability to do up to 3 transmit, 3 receive. We're also looking at communication and radar, exchanging sensor data. We actually have 3 vehicles through one of the projects with TxDOT that are equipped with radar, LiDAR, and cameras. And we're trying to put on some of these vehicles some of the millimeter wave test equipment so we can actually go around and make measurements and test and really show the validity of the ideas I'm telling you about here. So that's the key idea here. So a couple more slides on, just what's happening here. I mean, is the problem done? Well, it's not. I mean, I think that we've made great progress on it, but really, even though millimeter wave, it's nowadays really as a hot topic, but millimeter wave for vehicles, actually there's a lot of potential there. Now, it turns out that there was a lot of work done on this about 20 years ago, which we have tabulated in our little manuscript here that you can find online. But there's a lot to be done now. That work was done before a lot of developments in like CMOS and phased arrays. And so there's a lot to do with better ways of pointing the beams, estimating the channel, tracking the channel, even just very simple stuff, like where do you put the antennas on the car? Everybody wants to put like a big puck, like on top of the car, but the people that design cars don't want a puck up there because it looks stupid. So, but then if it's on the front bumper, how do you talk to the people behind you? So there's a lot of like interesting materials questions here to be addressed. I mean, we don't actually have a good understanding of channel models. I mean, if you're on a dirt road, how much reflectivity do you get off of the dirt versus asphalt versus concrete versus gravel? And then leveraging the site information, designing a communication system that uses sensing. I just talked about the base station in vehicles. A lot of the concepts could extend to us, to our handsets. Can we use information we derive in our handsets to make communication better? And then finally, integration into transportation simulators. And what I mean here, and this has really been a big challenge. I have a lot of funding from the Texas Department of Transportation. And I go and I talk to them about millimeter wave. And I tell them, and they're like, this is really great, but how many lives are you going to save with millimeter wave? I don't know, like 2? I mean, 100? I don't know. Or how much do you reduce the mean commute time in Austin if we have millimeter wave everywhere? Well, I don't know. But that's actually what they care about. They care about lives saved and mean commute time. A few other metrics too. But it's actually very hard to convert communication things like capacity, spectral efficiency, bit error rate into lives saved. And so we're trying to address that right now, but I think there's a huge opportunity there for collaboration with folks in transportation. And so what we've been doing at UT Austin has been, we've got a collaborative project with the Center for Transportation Research, and they do things like transportation modeling, human behavior analysis, policy and planning. They've been there for more than 50 years. And so our wireless center is working with them to really go beyond just the signal processing aspects and look at this from a complete system as it affects both the city, the drivers, the cellular providers, and just the people, the inhabitants of the city at large. And to do this, we've created a center where I'm the director called UT SAVES. So now I have to remember what SAVES stand for, Sensing and Vehicular Engineering Systems. It's one of those things where we came up with the name and then fit the words to the name later. And it's a partnership with Toyota, Huawei, National Instruments. We've actually just announced also that Fujitsu has joined, and then Honda, I think, has signed on the paperwork either today or tomorrow. So we're actually working with cellular companies and with transportation folks on not just millimeter wave for vehicles, but also these ideas of using machine learning, exchanging sensor data, and then understanding the impact of all of this in the transportation network. So with that, I hope that you have some appreciation for the potential for millimeter wave and for VDEX systems. And I'm happy to take any questions. Thank you. So I hope that was worth the 1 point of bonus credit some of you got to attend, or all of you, I should say. Yes.
This is our microphone.
Oh, there's a microphone in that box. That's really weird.
Yeah. Could you comment on the comment on the security issues of having cars relying on radio communications with other cars and with various base stations as they drive down the road?
Yeah, it's a big issue. And it's something that, of course, the DSRC protocol has a lot of mechanisms for securing communication, but it's not perfect. And people have been able to hack it. And it's one of the reasons that I think that that sensing is really critical here. Because I feel like if you're just relying on what other vehicles are telling you and not trying to get any kind of a sanity check, that is going to open yourself up to a lot of hacks. It's much harder for someone to spoof both the communication and the sensing and the radar trace and the position. So I think that's an issue. And generally speaking, I mean, it's very important. And we need security. And I think that using the sensing data is one way to improve the security. But yeah, we need more work on the security aspects.
Who else wants to ask a question?
Oh, there's a question over there. Oh, this is nice. Now I see it. Okay.
Could you comment on the implications or challenges for devices and material technology? For example, if you make transistors that work at millimeter wave frequencies, they need to be small, which means they have low power because of a volume density limit. So then to make power sufficient for operation, you have to gang them together, tune circuits, and it's always been a challenge. Do you have any?
Yeah. Well, I think, I mean, it sounds like you may know the challenges better than me, but that's basically the implementation. So for this to be really successful, we need a highly integrated solution, and that's going to have to use more conventional semiconductor processes where you get, transistors that don't operate efficiently, the power amplifier gain is small. So some of the challenges, I mean, it's engineering to get high gain, dealing with phase noise, nonlinearity, making large arrays, calibrating said large arrays, finding efficient techniques for doing beamforming. I mean, we could using lenses, we could be using this, optical up conversion, creating the multi-stream capability. So I think, I mean, there's a lot of difficulty in engineering, even things like the ADC. I mean, how can we make ADC operate with multi-giga samples per second with very low power? If I have 200 of those, I can cook a meal on that. It's not practical. So, I mean, we have research on very low resolution signal processing techniques, but then there's also opportunity for device people to come with, low power mixed signal techniques. I think, there's I don't know if I can be more specific, but I think that generally is a lot of opportunities there.
So my question is about, you're using machine learning, and machine learning is big data.
Yeah.
A lot of compute, and it could be unreliable, and if you're making decisions quickly on machine learning, you might not be saving lives. I'm saying it's an unreliable type of technique. So it means there's a lot of learning, relearning, reinforced learning, a lot of type of learning you have to do to be able to correctly predict whatever the right decision to make. So have you thought about it?
Yeah, so I think that's a fair question about machine learning and the issues associated with computation and latency. So machine learning, though, is, I mean, these kinds of approaches like deep nets, I mean, is the key ingredient of most of the automated driving vehicles that are done right now. And I mean, the back of the car is full of very special compute engines. There's NVIDIA, there's several different options, $20,000, $30,000, $40,000 worth of compute, sucking up power, sucking up gas, sitting in the trunk, generating heat. It's challenging. Now, some of the things that what I'm looking at is really machine learning to support the communication. So the safety of life is kind of a secondary thing because I'm trying to make the communication work well. And of course, I want that to support the safety of life. A lot of this can be done at the edge. So there's a lot of compute attached to the base station, and so that is where the high compute machine learning stuff is done, not in the vehicles. And I think that's even more promising than doing it in the cars themselves, because the vehicles over time, we want to have less sophistication. And there's also a lot of ways to solve that problem in the sense that, it could be that I train it's like a support vector machine, I parameterize a classifier, and so when cars come in this area, I send them, okay, here's the parameters of the kernel, you guys compute this regression, and so it's actually kind of a low compute thing. Figuring out said parameters and collecting all the data is done by the base station, but the vehicles do low complexity calculations. That's a thought I have. But really this idea of using machine learning with millimeter wave is pretty recent. There's not so many papers on it. There's a growing interest in using machine learning in general for wireless to configure wireless systems more efficiently. And I think there's just a lot of opportunity here because there's a lot of obvious structure. Vehicles are going the same roads. There's a lot of behavioral things like time of day that we could exploit. So, thank you.
Yeah, so I have a question about what kind of crowd effect of this millimeter wave technology on vehicles. So what I mean is that what percentage of vehicles should be equipped with this technology for the benefit of the technology to really become visible? Or the other way to ask this question is that if we have only a single vehicle equipped with this technology, can you identify some benefit?
Yeah, so this is something that we work on with the transportation folks, but the question has been answered quite extensively with DSRC, right? So when do we get the safety of life benefits, the transportation efficiency benefits, and it depends on what you're doing with the system. So they've shown for DSRC that you can start to get transportation efficiency improvements with as little as like 5% penetration. And the reason is that, like if you have, there's this phenomena where, I forget what it's called, but where kind of congestion propagates in a backward wave on a highway. You know, so a whole bunch of people stop here and they slow down, and then these guys slow down, and then these slow down. And you can use communication to kind of break that effect and stop it. So that's an example where you don't need a lot of penetration, because you just need a few people along the way to kind of control that. Some of the benefits I've showed you, I mean, you need higher levels. Like an automated intersection really only works if everybody's automated. So then we don't get the benefits from that. But the idea of putting the sensing on the base station, though, it helps a lot, because that's going to overcome the lack of sensing from the non-connected vehicles to a large extent. And so that's why I think it's really important. I mean, if you have a lot of millimeter wave base stations, one connected car, but the base stations have sensing, I think you can do an incredible amount of good versus if you just have, you know, the sensing on the vehicle. And then there's no one else to talk to anyway. So here, right, you're monitoring all the other stuff that's happening. And in the other case, you're just seeing what's around you in your environment. But, you know, really, I mean, the net benefits are not entirely clear to me as a function of, you know, percentage. And I don't know, you know, does it have to be 10, 20, 50? It just depends on what you care about. Yeah, I don't know. Yeah, I've never seen this box before. It's pretty cool. Yeah, throw it. Come on. Wow, look at that.
So for some like large cities, like say for New York as an example, where there's a lot of congestion from like pedestrians, since there would probably be a lot of blocking as far as if you try to use like the radar and everything, would you think it would be better for them to like kind of, I guess, change how the infrastructure is, like have the pedestrians like go over like a bridge or something? Or would there be a way to kind of like mitigate that with the, I guess, like how they sense with the cars, like, because I feel like there could be a lot of stalls with people, especially at like lunchtime, everyone's just like crossing the street, cars won't be able to move.
Yeah, that's a great question. I mean, that's one of the reasons I love working with the Center for Transportation Research, because they have a lot of understanding of sort of like people and their behavior. But I mean, this is really cool. You know, I can imagine going to like City of Austin and saying, you know, we need to build a bridge here because my millimeter wave signal is going to be blocked. So I don't want these guys blocking my signal. Probably they're not going to go for that. I have to say, though, that, I mean, people are potentially the death of automated driving at all, because we're so unpredictable on the streets. And so I mean, seriously, yes, you could imagine engineering the sidewalks, the pathways, so that people interact with the vehicles and the streets in a way that's better for them, for the safety of the vehicles, even for the wireless. Now, there's other ways to solve that problem, too. If I have the infrastructure kind of high up, the fact there's a lot of people here doesn't bother me as much as if the infrastructure is here and I'm blocking it. So there's different ways to engineer the infrastructure. There's ways to engineer where the people go. I think it's a big issue, though. And one of the solutions in what's called V2P is vehicle to person. And the idea there, this has been pushed by Qualcomm and Honda, is that we also have a DSRC unit in our phones. And so as we are walking, we also broadcast position, and then the vehicles can use that to avoid us. But of course, that's not efficient, because then everyone's just like, I don't have to look both ways, and you just wander into the street, whenever they feel like it. And that's not going to be good for everyone either. But yeah, I don't know. It's just a good question. So, any other questions? I'll try to answer one of these at some point.
There's a phone application called Waze that was developed in Israel, where you input, let's say, a pothole that you passed by.
Yeah, I use that like every day, actually.
Yes.
Yeah.
Will the vehicles that are developed with this technology able to perceive that, or let's say a cop is on the road next to it? Yeah. Will it be able to communicate that information?
There's a lot of stuff that could already be done. I mean, okay, so I do have to say, I do seriously use Waze quite a lot, and in one of my cars I have a radar detector, and it pisses me off to no end that there's no interaction between the two, because sometimes the radar detector is actually detecting a cop, but then why do I have to, push a button that says there's a cop here? I mean, it should just know, or it should at least ask me, hey, is there a cop here? We're detecting the radar, right? And then, why can't I just have a camera on my car to detect where the cops are? I mean, I think about where the cops are a lot, obviously. And so I think there is a tremendous opportunity to fuse that data. And that's just a case where, man, they could solve it already. The radar detector is Bluetooth enabled. I don't know why it doesn't work. But we'll be able to do so much more with millimeter wave. So the example I gave about the imaging is much beyond the pothole. So that pothole may be a valuable landmark for me, okay? When I hit that pothole, I know I'm exactly at this GPS coordinate. So the structure and everything is what's gonna be part of that 3D map. And the pothole and everything else will be part of it. And so you can imagine that Waze goes many levels beyond that. And so maybe there's like a layer on top, like the auditorium here doesn't change every few years, but then okay, right now everyone is in a certain spot, and so I get an update, and then everyone leaves and I get another update. So I think this principle is extensible to this new paradigm with lots of data. Yeah, I don't know. I think I'm answering any question here. Can I have like a simple question? Yeah, Dennis has got the box back there. Yeah, it's a question in the front here.
Oh, wow.
Yeah, throw it. Come on. Let's see you do it.
Test my arm.
Wow. What happens when someone gets hurt with that thing? It's foam?
It's foam, yeah.
Sure it is.
What if like a van had a mirror finish? What would the LiDAR do then when it tries to read lasers off the mirror finish?
If what had a mirror finish?
A van.
The van.
And you were behind it.
Well, it reflects pretty well off the van if it has a mirror finish.
Really?
Yeah, I think that would be pretty good, actually. And yeah. I mean, the worst case is actually when there's mud on the LiDAR. Then you're screwed. And you actually do need, a little wiper or something on it. That's a big challenge. That's one of the main problems that LiDAR doesn't work well in dust, dirt, bird craps on it, doesn't work.
So in cities where this would be obviously most beneficial, the fact that millimeter waves can't travel through buildings, right?
Yeah.
Will this be practical to deploy base stations every block?
Yeah. Yeah, that's a good question. The thing is that if we're going to have millimeter wave, it's probably going to be deployed every block anyway for exactly those reasons. So if we want a millimeter wave in cities, it's got to be like the most of the numbers we look at on our papers is like 150 meter inner sight distance. That's every 2 a block, 1 a block. So if they're small, if they're deployed on lampposts, it's not a big deal. If it's like, these humongous base stations, of course you couldn't have that everywhere. But I don't view that as a major limitation, because I just feel like if we're going to have millimeter wave, we're going to have it anyway, the density. So and it's just going to be another reason to have it. Financially, well, no. So the finances of base stations is very interesting. You have CapEx and OpEx. So you have the capital expenditure to acquire the site, and you have the operating expenses. Now, what I see here, and I've been telling, one of our sponsors is Crown Castle, and they own more than half of all of the base station sites in the US. And so the city of Austin owns these lampposts, let's say in Austin. And so right now the city doesn't have a lot of incentive to put a base station there because they don't want people climbing up the pole causing security risk. But if you go to the city and you say, hey, if you let me use the pole, I will tell you about traffic flow here so you can time your lights. Then they might be like, oh, that's actually good. And in fact, the city has told me that if they could get data, they would be happy to share the infrastructure. So then you eliminate the need to build and permit and site a new tower. And then you've got power and such. Power is not a very big deal. So it's really it's about access to that pole. And so I think if you can make it worthwhile for the city, you will be able to solve that problem in a surprisingly inexpensive way. And in fact, I think that's the way that millimeter wave may happen. If we don't have that, I don't think it is going to happen, because that's the reason that small cells haven't been successful. They're too expensive. The cities are all like, ooh, base station, I want $2,000 a month. Where you're like, well, but the base station's only this big. It's not this big. Oh, I don't care. I want $2,000 a month. So there has to be incentive there, and I think that this is actually going to give them the incentive to do it. The sensing plus the base station. Thank you.